So now we are going to learn about expectation maximization algorithm, or we commonly refer to it as EM algorithm. It is mainly used to derive MLEs in situations where certain data is missing. So in the last week, we studied how to obtain the maximum likelihood estimators with the common method that we have. So there we assume that all the observations in the dataset was available to us. However, when you are dealing with huge amount of data, you might come across situations where certain observations are missing. In that case, you cannot simply apply the original method of maximum likelihood estimation. For that, we have the EM algorithm, which is mainly used whenever you have missing data or missing observations in your dataset. To understand this, let us consider a random sample of size n from a population whose PMF is given to us. So x1, x2, xn, this is a random sample. Now, in this random sample, what might happen is that some of the observations might be available to us. Okay, so these, suppose out of n, x1, x2, xm, m observations are available, and the rest of them, that is n minus m, starting from xm plus 1 to xn, these are missing values of the random sample. So let us understand what it is. x1, x2, xn, xm first suppose, and xm plus 1, and so on up till xn, right? So if these are the random variables representing your random sample, so basically x1, these small letters are used for the realized values. xm plus 1 and so on, these would be the corresponding realized values. So here, what we are saying is that your vector x over here comprises basically of these elements which are known to us or observed, and these are the unknown ones that are missing. So basically, your realized vector, this composed of x observed, and it is composed, the second one is x missing. Now, corresponding to the entire sample, that is x, you will have some likelihood function x, right? So corresponding to the entire sample, you have f x theta, this is the likelihood function, and the likelihood function corresponding to the observed data is f x observed given theta. Okay, so these are the notations that we are first understanding, and then we will move on to the actual problem. Now this function, this likelihood function that we have, which is a likelihood function of the observed data, so it means it can be observed and it can be calculated. However, we cannot compute this likelihood function of the entire sample because it involves certain missing observations also. So it cannot be directly computed, and we need to estimate it in order to estimate your parameter theta. Okay. And how do we estimate this parameter in the scenario of this x, given that you have only certain observed values while rest of them are missing? Okay, so here you have m are observed and n minus m are missing, and from based on this, like the likelihood function on based upon this, you have to find out the estimate for the parameter theta. Okay, so this is what we do in the maximum likelihood estimation also. We find out the likelihood and then we try to maximize it. But here the situation is different because the likelihood function has certain missing observations also. So in order to deal with that, let us see how do we do that. Let us consider the log likelihood function of x observed. This is the observed data. We are considering the log likelihood function. Now what is this function over here? This is basically the likelihood of observing the given data, this one, for a particular value of a parameter. Likelihood also in general, if you can recall, then I mentioned that likelihood basically tells you that if you have observed this sample, then this sample has arisen basically because of which parametric value, or which value of the parameter has given rise to this particular data set. So in this case also, this L theta is basically the likelihood of observing the given data, this one x observed for a particular value of the parameter theta. Now what we are doing over here is, in the first step, if you see, this is nothing but log likelihood function. So we have written log, and we have written this f x observed given theta. This is the likelihood function for the observed data. Now what we are doing over here is, we are trying to integrate this. If you see, x missing is there, we are in this integral is over x missing, and here we are integrating it with respect to the missing data. So this integral basically over here, this represents the sum of all the possible values of the missing data, taking into account the uncertainty due to the missing values while you're working with your observed data and the parameter theta. Okay, so this basically, if you see over here, this is the joint likelihood of both observed and missing data. Okay, and now you are marginalizing over the missing data. When you are integrating it, you are marginalizing it over the missing data. Okay. Now in the next step, if you see, we have multiplied and divided by this term over here. Okay. Here you can see that this term is same which comes over here. This term is same. We have multiplied and divided by this conditional probability. Now what is this conditional probability? It's the conditional probability of the missing data given the observed data and the previous estimate of the parameter, that is theta suffix old. Okay. Now this can also be written as the expectation. So we have written expectation of this quantity over here given x observed and theta old. So you are given the observed data and the previous estimate of the parameter. Here, if you see, we use the Jensen's inequality, which says that if you have a concave function, so if phi is some function which is convex or concave, so let me write for convex and concave simultaneously, then expectation of phi of x, this is going to be greater than, and in concave case it is going to be less than phi of expectation of x. Right? So if you look at the concave situation, okay, so if you look at this concave one, so it means we are talking about this inequality over here, and we have log basically, which is your concave function over here. So log of expectation, this is greater than equal to, you can take expectation outside and you are left with this log term. So now what you can see over here is that since it's a log, so it can also be written as, if you see here, it can be written as log of this numerator. Here you have the numerator and here you have the denominator term. Okay. So this basically, this numerator over here, this first term, this is referred to as EST, or the expectation term over here of theta and theta old. And this one, we can keep it as it is because ultimately we will not be using it. The reason is that our parameter theta is only present over here. We do not have any parameter theta in this case, in the second term. So there's no point in trying to maximize it. Okay, so here, from here, now our interest will only be in this first step, that is over here. So x observed, this is the observed data and this is the missing data. Okay, so this expectation term over here, E step that we say of the EM algorithm, is estimating this theta. So we take expectation of log of this quantity given the observed and the old one. So it's a probability of the missing data given the data that we see, and it's not evaluated at the same theta but at some new random value of theta old. Okay, so it is a function. Basically, you can see that it is a function of both theta and theta old. Now, what we do in the maximization step, that is the M step. Now, finally, we maximize this thing with respect to theta. That is, the new theta would be maximizing this particular E step. Okay, so what we have done overall is that we started, so we were given a data set, right? The data set that we had over here had certain missing observations and certain observed values, and based on that we said that if I have to find out the estimate for the parameter, in that case what we do is that we start with the likelihood function for the given data and for the given value of theta. With that we begin and we just solve it step by step, and finally we reach your E step and your M step, right? And that is basically your EM algorithm, which involves these two steps. So we are first going to perform this E step, and the next one we are going to solve this maximization step. So let us consider certain examples in order to understand what is happening over here. Let the complete data vector, that is x observed, and this be a random sample from a normal distribution. So basically we are considering a normal distribution over here. In this case, we know that what will be the likelihood function in this case? Likelihood function we have seen multiple times because the PDF is 1 over sigma root 2 pi e power minus 1 by 2 x minus mu by sigma whole square. So now you can see that from here, if you have n such terms, so you will have 1 over 2 pi sigma square power n by 2 this side, and e power minus 1 by 2 summation xi minus mu by sigma whole square. And this term basically you can write it as summation xi square minus, if you are basically expanding this, it will be minus 2 mu summation xi plus n mu square. Okay, so this is what we have done earlier also. It's very easy to see. Next, what we have to do is we have to take the log of this, okay, likelihood function. So log of this would be minus n by 2 log sigma square and minus n by 2 log 2 pi. So that is over here as a constant. This side, it would be minus 1 by 2 summation xi square. So this term would come. From here, you would have again summation xi. So mu by sigma square would come, summation xi. And finally, the last term n minus, because here it is minus and this, minus n mu square over 2 sigma square. Okay, so this is the log likelihood function. So after this, we are ready to perform your E step. What do we do in E step? We have to consider the expectation of this basically. Okay, so this is by definition that expectation of log of x observed. This is the log likelihood function of the entire sample given the observed data and the old parameter estimates. Okay, so we are just copying it from the previous slide. So minus n by 2 log sigma square. You have the second term over here, minus 1 by 2 summation xi square plus mu by sigma square summation xi, and this one. Okay, now when I am taking the log, this term, if you see, when I'm taking the expectation inside, so I have to solve it for each term. Okay, so let us first see what are the constant terms. So if I take the expectation of this term over here, this is a constant, so we will just have same term coming over here, minus n by 2 log sigma square. And also, if I consider the last term, then also I would have the same term coming here, minus n mu square over 2 sigma square. So what we are left with is solving these two terms. Okay, so we are left with this term and this term. So let us see how do we do that. So I can add one page over here and see. Okay, so let me just show you how it is done. So I have to find out expectation of minus 1 by 2 sigma square summation xi square, where I goes from 1 to n. So let us solve this. So obviously minus 1 by 2 sigma square is going to come outside, and we do not have to worry about it because anyhow it is present over here. So minus 1 by 2 sigma square expectation of summation xi square. Now it is the summation of n terms xi square, right? So this basically means that, so let me just ignore minus 1 by 2 sigma square and just move ahead with this term only. So I have expectation of this. This is basically from n terms basically are comprised of first m observed values, and then we have the remaining from m plus 1 to n, we have the remaining missing values. Okay, so I can write it in this way also. Now let me take expectation inside. Now when you know that these are the observed values, in that case, what will happen? It would be just summation xi square because these are observed. These expectation would remain the same, summation xi square, plus in this case what it will be, summation I going from m plus 1 to n expectation of xi square. So again this would come down. It means we have n minus m terms over here, right? N minus m terms. And what is this expectation xi square? We know that expectation of xi square is nothing but variance sigma square, because expectation of x square, we know that if I have to find expectation of x square, it would be sigma square plus mu square. Since here we are given the old parameter values, so we will substitute those. Okay, so here I have not written this part that x observed, so you can understand it in that way only. Okay, so these are the given things that we have. I've simply simplified it for you to understand. So what you have obtained over here is, if you compare this one, so summation xi square plus n minus m times sigma square old plus mu square old. Okay, so the first term is done. So here we have obtained expectation of summation xi square. So this term is already done. So now let us see what will happen if I take the second term over here. Okay, so plus mu by sigma square is already there. So let me just write expectation of summation xi, I goes from 1 to n, right? So here this is basically, so you can understand that it is for these given things, right? So observed is given and theta old is given to us. So based upon that, we are trying to find out the expectation. So summation xi, I is from 1 to m, xi plus the remaining one would be m plus 1 to n. So basically we are separating out the terms which are observed and which are missing, right? So now since m these are observed values, this one, so it would be just same as it is, even if we are taking expectation. I1 to m plus here it would be n minus m times expectation of xi, and we know that since it is coming from normal distribution, each of these xi's would have expectation as mu, right? Or rather we write mu old over here. So we can just see what is happening over here. We have written summation xi plus n minus m times mu old. Okay. Now in the m step, what we have to do is we have to differentiate this e step with respect to both the parameters that we have. That is, we have to differentiate with respect to mu as well as sigma square also. Okay. So for that case, in order to do that, let us see how do we get this mu nu. So to understand this, let me add a page, a blank page. So first of all, let us differentiate it with respect to mu. When we are differentiating it with respect to mu, you can see from here that there is only third and the fourth terms. These are the only terms which are contributing. The first two terms would eventually be 0. So if I write it, it is mu by sigma square and it is summation xi, I from 1 to m. So this is I1 to m, sorry. Right? M plus n minus m times mu old. This is present. Okay, minus n mu square over 2 sigma square. Fine. So we have to differentiate it with respect to mu. When we are doing that, we can see that the first term would be 1 over sigma square. So differentiating with respect to mu. So it is 1 over sigma square. And here it would be just summation xi, I from 1 to m plus n minus m times mu old minus n over 2 sigma square into 2 mu. Equate that to 0. Right? 2 and 2 would cancel out, sigma square would go away, and what you will be left with is that summation xi, I from 1 to m, these are the observed values, plus n minus m times mu old. Again, this would be the old parameter estimate, and divided by n, this is basically your new maximum, or you can say that new estimate for the parameter. Okay. So this is, you can see that this is based upon just your observed values and it does not involve your missing observations. Okay. And this is what we have as the result for your m step. Likewise, we have to differentiate now with respect to sigma square also. Okay. So let us first write what is given to us for sigma square. What is the likelihood function that we had? So I can add a blank page. So before that, let me just write over here what it is. So we had the terms as minus n by 2 log sigma square was there, minus 1 by 2 sigma square, and this summation xi square I1 to m plus n minus m times sigma square old plus mu square old plus mu by sigma square summation xi, I from 1 to m plus n minus m times mu old minus n mu square 2 sigma square. Now since we have already obtained the estimate for mu, that is mu nu, we can replace these mu's with mu nu now. We can just write this. Now let us differentiate it with respect to sigma square and see what do we get here. So when we are differentiating it, so the first term would be minus n by 2 sigma square plus here it would be 2 sigma raised to power 4, and this entire term would come, right? If I just write it over here, and in the next one again it would be minus mu nu over sigma raised to the power 4, and this summation xi term would again be here. Okay, this term would come minus, or you can say plus, it would be n over 2 sigma raised to the power 4 mu square nu, right? Now when you equate it to 0, what you have is, in the denominator you will have 2 sigma raised to the power 4 that goes on the right hand side and becomes 0. What you will be left with is minus n sigma square plus summation xi square, the same terms that we had earlier, summation xi, so this one will be square over here, summation xi square plus n minus m times sigma square old plus mu square old plus, or you would, here it would be minus times 2 mu nu, because here if you see this term over here, this is again mu nu, right? So this one here would be, yeah, so if you look at this term summation xi plus n minus m, so this is the numerator, right? So this is basically your numerator would is nothing but n times mu nu. Fine, so we are replacing it, so it would be minus 2 mu nu into n times mu nu plus n mu nu square. This is equated to 0. And now when we solve this finally, so these two terms, n sigma square would go to the right hand side, and sigma square finally would be summation xi square I from 1 to m plus n minus m times sigma square old plus mu square old. Okay, this whole divided by n minus, because this is the term that we are left, so minus 2n mu nu square plus n mu square nu, so it means that terms would cancel and what you are left with minus mu square nu. So this is your new estimate for sigma square, which is given over here. Okay, so you can see that it is different from what you have obtained in the maximum likelihood estimators, because there you had x bar and n minus 1 over n s square. So this shows that if you just ignore that there are certain missing observations and you apply the original MLE, then your results would be wrong. So it is important for you to understand that how do you deal with the estimation concept whenever you are having missing observations in your data set.